Hey everyone, welcome back to another video of mine, where today we're going to be solving Leetcode problem 994 titled Rotting Oranges. So it actually just dawned on me a few hours ago that I actually haven't solved any BFS or DFS or even any graph problems on this channel, and this is actually a very common technical interview question, and so I thought this would be a great problem to go over on this YouTube channel. So yeah, with that out of the way, let's just go ahead and dive into the problem statement. So we're given an m by n grid where each cell can have one of the three values. Either it can have a value of 0, which represents an empty cell, 1 that represents a fresh orange, or 2 that represents a rotten orange. And every minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. And we have to return the minimum number of minutes that must elapse until no cell has a fresh orange, and if this is impossible, we'll simply return -1. And what 4 directionally adjacent simply means, it basically means left, right, up, or down, or basically any non-diagonal adjacent movements that are actually next to one cell within our input grid. So in example 1, as you can see for the example 1, they actually visually depict how this would work within our input grid. And our grid itself is just simply nested lists within a larger array that in this case is going to be 2, 1, 1, 1, 1, 0, and 0, 1, 1. And we would output 4 because that is the minimum number of minutes to actually infect or rot every single fresh orange that's actually present at the beginning of our input grid. And you can see how the process actually works as we basically rot every single adjacent cell from each rotten orange within this grid, right? And ultimately, it's going to take minute 4. It's going to take us 4 minutes or up till minute 4 to actually make every single orange in this input grid rotten. Okay, so in example 2, applying that same logic, we have a grid of 2, 1, 1, 0, 1, 1, and 1, 0, 1, and we'd output -1 because we can't actually make every single orange rotten because the orange in the bottom left corner of basically row 2 column 0 is never actually rotten because rotting only happens 4 directionally, basically left, right, up, and down, or vertically and horizontally, but not diagonally. And so it's impossible to actually get to that cell from our current rotten oranges and actually infect that as well. And so basically it's going to say fresh after the algorithm is done. And in example 3, we have an input grid of just one row, which is going to be just 0, 2, and so we'd output 0 because we only need 0 minutes to actually infect any oranges, because since there are already no fresh oranges at minute 0 itself, the answer is just 0. We only have one rotten orange and one empty cell, and so we don't actually have any fresh oranges to actually infect, and so this would be 0 minutes needed to actually infect all the non-existent fresh oranges. So I will give you guys a few seconds to kind of just go over this problem in your head and think of a solution, and then in a few seconds I'll tell you guys how I would optimally solve this problem. Okay, so this solution can actually be tackled for this problem using a breadth first search, or BFS algorithm, which is actually ideal for problems involving spreading processes for grid inputs like rotting in this case. So we'll actually use a queue to perform this BFS by starting by just enqueuing all of the rotten oranges, and then I'll actually process each rotten orange level by level, making adjacent fresh oranges that are basically just 4 directionally adjacent as rotten and adding them or their coordinates to the queue. And the number of levels we actually process will give us the number of minutes required to mark every single fresh orange for every single BFS level as a rotten orange from there. Right, so the variables and data structure that we're going to actually be using for this problem is just going to be obviously the grid input, where the 2D array represents the grid, and then a queue, basically FIFO, or first in, first out order, to store the rotten oranges and process them, and a directions array to help move in the 4 adjacent directions, basically up, down, left, right, as we talked about before, and a fresh count to actually track the number of fresh oranges, and then finally a variable, just minutes, to actually track the number of times or levels it actually takes to rot all the fresh oranges. So just for best practice, even though I know all of these modules, libraries, and or dependencies are already installed in Leetcode before we actually start coding them up, let's just do this for best practice and just for simply good practice. So we'll say from collections, we'll import the double-ended queue or DQ data structure. Okay, and honestly, for Leetcode, like I talked about before, this isn't really necessary. It's already all installed and imported from these modules and libraries. But just for good practice, let's just do this. And yeah, once I do that, now I actually want to initialize my two variables, rows and columns. to actually access them with all the different cells in my input grid. So what I'm going to do is I'm going to set rows and columns. I could call this columns. I'm just going to call it calls for easy access. And I'm going to basically set it to be respectively equal to the length of the grid and the length of the grid at 0. And in Python, if you guys aren't aware, to actually just access the number of columns and rows within an input grid, we can simply set rows and columns to be the length of the grid, or the number of rows, and length of the grid at index 0, or basically the number of columns within our input grid. And once we do that, after we initialize these two variables, we actually want to initialize our queue. And I'll literally just call it queue. I think that's how you spell queue. I'm not 100% sure. Correct me for any of you English proficiency users or English majors. I think that's how you spell queue. I'm not 100% sure. And I'm basically going to initialize it to be an empty queue, right? And again, correct me, English majors, if I'm wrong. I really don't know how to spell queue. It's a pretty tough word. But once I actually initialize this queue, now we'll actually initialize a variable fresh that basically tracks the total number of fresh oranges present in the grid for every single BFS level. And of course, we'll set the fresh oranges to be first at 0, because we haven't actually processed or parsed through our input grid yet. And once I do that, now let's actually have our nested loops to iterate over every single cell using our rows and columns variable in our input grid. And so I'll do this like so. We'll say for R, or basically for rows in the range of the rows in my input grid, or basically length that grid. And then I'll say for nested loops for C, or columns in the range of length that grid at 0, or basically all the different columns as initialized our columns variable. Now we'll actually check. This is basically a nested loop to iterate over every cell, and where R represents the current row index, and it iterates from 0 to rows minus 1, and C represents the current column index, while it iterates from zeros to columns minus 1, right? And once I explore every cell using this nested for loop, what I'm going to do is I'm actually going to check if the current orange or cell that I'm looking at, if it's actually rotten or not. So I'll say if grid, if grid at R at C, or basically any index RC, if it's actually equal to 2, as we talked about in the problem statement, that means it's a rotten orange, right? As you can see right here on this line. And so if it's a rotten orange, we want to actually add these coordinates as an already rotten orange to our double-ended queue. So we'll say q dot append the coordinates R and C, okay? And once we've actually done that, we actually have to have another else if, or conditional check, to actually check if we're looking at a fresh orange. And so outside of this if statement, I'll have an else if, or an elif statement. If grid at R at any index C, if that's actually equal to 1, that indicates that this is a fresh orange. And so we want to increment the number of fresh oranges we've seen by 1. And once we've done that, once we actually exit this for loop, we want to actually have our basically kind of base case in this problem. If the fresh, or the number of fresh oranges we found for every single cell, if that's actually equal to 0, then there's literally no fresh oranges in this input, and we can automatically return 0, right? And this is basically a simulation of example 3, where we don't actually have any fresh oranges in our input. They're already all empty or rotten, and so we can simply return 0, because if we don't have any fresh oranges, it doesn't take any minutes, or basically 0 time, to actually infect the non-existent fresh oranges that are actually already present within our input grid. And once we actually cover that base case, after we return 0 immediately if we don't actually have any fresh oranges, now we can actually initialize our minutes variable, which ultimately is going to be what we return. So we'll set minutes to be 0. That keeps track of the number of minutes or time we actually take to infect all of the different 4 directionally adjacent rotten or fresh oranges for every level of the BFS algorithm. So we'll initialize that to be 0, because of course we haven't actually scanned through the input array nums, or the input grid yet, and so of course it's going to be initialized to a minutes of 0. And now we're going to actually initialize our directions array, right? So we'll say directions to be basically the different coordinates we can have that are actually 4 directionally adjacent to every cell that we're looking at. And so this is basically going to be an array consisting of nested tuples, and this is going to be basically either 1, 0, and then either negative 1, 0, and then either 0, 1. And finally, for the last way we can move is going to be 0, -1. And essentially what these ones and zeros or binary tuples are actually indicating is that we create directions array that actually store all of the four possible movements for this specific cell, where basically 1, 0 is basically moving down, -1, 0 is just basically moving up, and 0, 1 is moving right, while 0, -1 is moving left. And this basically helps in checking the adjacent cells of each rotten orange. Now we actually have to have our while loop that monitors and validates our Q and our number of fresh oranges for every BFS level, right? So we'll say while a Q and the number of fresh oranges, while it's actually greater than 0. So basically what this is checking is, this is kind of our main loop that runs as long as there is actually rotten oranges to process in the queue, and the fresh oranges left is actually still greater than 0. In that case, we can increment the number of minutes taken by 1. And once we do that, now we'll actually have, basically at the start of each level of BFS, we'll just basically increment the number of minutes by 1. Well, each level of BFS represents 1 minute passing as it spreads the rot to adjacent cells for every fresh orange that are 4 directionally adjacent for each specific cell at index R, index C, right? After we do that, now let's just use a underscore as our iterator for now. It doesn't really matter. We'll say for underscore, whatever we can use as a placeholder for this iterator, in the range of the length of the queue itself. Okay, length of the queue. I think I spelled it right. Please correct me if I'm wrong. Again, for that in the range of the length of the queue, we'll basically get R and C to be the Q dot pop left. Okay, and essentially what this is doing is that we actually process all of the rotten oranges at the current level, and the for loop runs for each rotten orange currently in the queue. And we'll use q.popleft to remove and return the coordinates RC of the first rotten orange in the queue. Okay? And now, after this, we'll have another for loop indented within this for loop, and we'll say for dr, directions of rows and directions at columns, dc, in the directions array that we can actually possibly move to for all different 4 possibilities. We'll actually say nr and nc to basically be r plus dr and c plus dc. And this may be a little bit confusing for you guys right now, and to kind of just recap what this does is, for each rotten orange R, C are the coordinates, we check its 4 adjacent cells. dr and dc are basically the changes in the row and column base of the directions array, while nr and nc are the new row and column coordinates of the adjacent cell, as basically r plus dr and c plus dc. And now, what we want to do is we're going to basically have this super long if statement, or conditional, basically checks if 0 is still less than or equal to the number of rows, which is less than the rows in our input grid, so basically it's still within in bounds, and 0 is still less than or equal to the number of columns, or the current column index that we're looking at in this iteration, which is still less than columns, so it's still within bounds of the number of columns in our input grid, and grid at index R at index C, or basically this specific cell in this iteration, if that's actually equal to 1, or if it's basically a fresh orange, we want to actually set grid at nr at nc to basically be equal to 2, right? Basically be marked as a rotten orange. And then we'll actually append those coordinates to our double-ended queue. So we'll append the coordinates of nr and nc, and then we'll actually decrement the number of fresh oranges we've actually seen by 1. Because of course we marked 1 more fresh orange in this BFS level to a rotten orange, as we saw on line 24. And once we've done that, to kind of just explain what this code does again, we'll basically check if the adjacent cell nr at nc is within grid bounds and contains a fresh orange, or basically if grid at nr and c is equal to 1. And if that's actually true, we'll mark it as rotten as we did on line 24. We'll basically set it equal to 2, or basically a rotten orange, and add its specific coordinates, or basically RC, or NR and C, to the queue, and decrement the number of fresh oranges that we've seen by 1, right, where the coordinates are basically NR, NC. And once we've done that, we can basically exit our while loop to actually check for the iteration and inbounds check or validation check for all the different cells that are fresh oranges that we actually have to still rot. And once we've done that, we can simply return the minutes if the number of fresh oranges we've seen, if that's actually equal to 0. Of course, if it's not, then in that case we can simply return -1, which is kind of our second base case. And unless I made any syntax errors here or anything like that, this should be completely fine, and this should be accepted, but I probably misspelled something. Okay, yeah. So clearly I misspelled something here. So let me just go back and kind of just decode this code here. Alright. Yep, we'll get a DQ, we'll get fresh. Find the region of the rows. Let's see. Yeah. Fresh equals 0, return 0. Minus equal to 0, direction is equal to 1, 0, 1, 0, 0, 1. Okay. Yeah, this is just normal. I always really make these dumb mistakes. Now I have to just sit here kind of just decoding this in the middle of the video. But yeah, directions C plus DC. If 0 is less than or equal to NR, which is less than the rows, and 0 is less than NC, and greater than C. Okay, yeah, so this should actually be NR and NC, because these are the new coordinates that we're actually looking at, instead of just R and C. And now this should be completely fine, and this shouldn't be accepted. And as you can see, it is just about as efficient as you can get. So yeah, that's basically how this works. And runtime complexity wise, this code is going to have a time complexity of big O of n times n, where n is the number of rows and m is the number of columns in the grid. And this is because we actually process each cell once, either as a fresh or rotten orange, within each level of the BFS algorithm. And space complexity wise, this is also going to be a big O of n times n, because in the worst case, we might store all of the rotten oranges in the queue at once. And that's because we're iterating over every cell in the grid once, and so we're storing up to all of the rotten oranges in the queue, or basically all of their corresponding coordinates at any time. So yeah, that's basically it. That's basically how the BFS algorithm actually works. Quite a lot of code, and quite some hefty decoding, but honestly it's not too bad unless if you really understand it. And yeah, so if you guys really understood this problem and liked this content, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.